wait, hold it. There's no slides.
Oh, you're right. Okay. Can you help with that? I still am not getting that. Sorry about that.
Just need power. Maybe power, huh?
Oh, maybe power. Oh, there we go. We didn't turn the power on.
Yeah.
Well,
I thought it was turned on. Yeah.
well, then they turned down the lights too.
We're just waiting for the slides to appear here on. Okay, just.
Hello. Everybody hear me?
Yep.
Hello?
All right.
Please clean filter. You're on.
Hello, my name is Bobby Hilster, and I am your particle model. Oh, whoops, wait a minute. That's the wrong introduction. That's the introduction to my YouTube channel where I explain the particle model that David and I are working on. And since I goofed up, because you realize I just goofed up, really. Anyway, if you want to watch any of those videos and learn about the particle model, you use particle.guru.com.
No, youtube.particle.guru.
That.
youtube.particle.guru.
Okay, I don't even know my own channel. And I don't apologize because somebody was telling me we got to market our stuff, so that was my marketing strategy for today. Okay, back to the presentation. The title of the presentation is Dark Matter versus G. So we're going to compare the two and see what we can come up with. This is a typical graph. I've used this one back in 2009 when I first talked about dark matter, but there was something I didn't see in the graph, and we're going to talk about that today. But the blue curve is the measured values of the velocity of the speed of the stars as you go from the center of the core outward. And you'll notice, though, that even though the blue curve is measured, the Keplerian calculation, according to this graph, is way too low at the edge. The measured value is much higher, and that needs to be fixed. Well, this isn't the only one that is available to be used. Here's one from the University of Arizona, very similar. Different data, but it kind of shows you the data points it used to plot the curve, which I thought was interesting because the first one I had there doesn't have the data points. And then there's this one from the Ohio State University. And they I don't think they got the red curve right. At least it didn't agree with the first one. And they have a curve, but you can see that the curves are there, but they're much smaller. I can't explain all these differences. I didn't attempt to explain it. Just to show you that's based really on the data, getting the raw data, judging for yourself what is right or what you think is right and wrong and plot it. It's probably the best thing. Obviously, I did not do that. But I'm basically going to use the first curve. The first thing I'm going to do is look at the galaxy itself. And at the center you have the core. And from one edge of the core you have one major arm, and from the other edge of the end of the core you have another major arm. And in between you have some smaller arms between the first and between the core and the first arm, and between the second arm, the first arm and second arm. Interestingly enough, they do show our solar system, which is right down here. I put the red dot right over it, and that's where our solar system. And they have a polar grid laid on top of that, which I'm really not going to discuss. I just want you to note that our solar system, as you go from the core through a space, through the arm, is in that second space. So now we're going to visualize the galaxy using the blue curve. This is what I didn't realize 9 years ago when I first did this. And what you have here, and I'm just going to walk right straight through it, is a zero velocity at the center of the core. And so you can imagine yourself on top of the spinning core. You're turning, there's no velocity. As you go to the edge of the core and the core is turning, you have a higher velocity. And you start out with zero, you go to the edge of the core up here, and you have a higher velocity. Then you have a gap. And we all know that the force of gravity drops by the inverse square of the distance. It doesn't come far from this curve, but you can see it's dropping like r squared. Then you go to the first arm and it increases. The velocity increases, and you get to the end of the first arm and in that first gap, and now you're right where our sun is. And I pointed out that earlier, that that's where the sun is. That's the one gap, and then this is the second arm, and off it goes. So you can actually see the galaxy in the curve, which I think is quite amazing in itself. Especially since it took me 9 years to see it. Okay, so what what they do is they use this velocity equation, which is you probably all know well, and they use it to calculate the velocity of the stars at the edge of the galaxy, and the velocity is too low. And so they have to explain this. What they need to do is increase the velocity by, you can increase g, you can increase the mass of the galaxy, or you can decrease the distance. Well, being mainstream, they're not going to change g. If there's any constant that they rely on, many people rely on, that's a constant. That doesn't change. The distance could change. You could remeasure it and get a new number. But changing it enough to change that distance is probably not going to happen. So there's only one thing left. There's m. What if? You can see them thinking, what if there's more matter out there that we don't know about? In the end, I looked this up in Wikipedia, the standard model cosmology indicates that there's the mass energy of the ordinary matter is about 4.9%, and the dark matter and dark energy constitutes 95%. I haven't verified any of those numbers. I'm quoting what they say. That's how much dark matter is needed. You got to add 19 times the mass that's in the equation to get the velocity up where it needs to be at the edge. So they invent dark matter to do what? Protect Newton's equation, the Keplerian equations, and keep the constant, the gravitational constant. Constant. Now I'm going to talk about shielding, which is actually more to the point. I almost should have titled this shielding, because I'm going to use shielding to explain the curve. Georges Louis Lesage, about 250 years ago, had a theory. He proposed it. It survived for a while, got quite a bit of attention, then died. If you go to the internet today and in Wikipedia, look up Lesage and his theory, you'll see it's totally discredited. I just saw a video that Richard Feynman made in the 60s at Cornell, and he mentioned this theory, and he mentioned about drag, and he says, that's it, don't worry about that, that's not valid. I jokingly say to myself, well, that's why I picked it. Mainstream thinks it's invalid, so maybe there's some value to it. Okay, so, but Lesage suggested, this is the way he phrased it, that ultramundane corpuscles, which are particles, are coming at the Earth from all directions and passing through the Earth. Some of them would interact and push the Earth, leaving fewer of them to pass through, and this loss is called shielding. It sets up a net force, differential force that is the cause of gravity. In other words, you lose it going through the Earth, you don't lose it here, and now you have the net force of gravity just by shielding, even with one object. Good book on this is Pushing Gravity, printed by Aperian and edited by Matthew Edwards. A lot of information available about different aspects of pushing gravity. In fact, in that book is where I found Majorana's experiments. In 1920, Majorana did a series of experiments. The first one, he used a mercury cylinder of 104 kilograms, and he used it as a shield. And then he used lead blocks weighing 9,603 kilograms. And I'm not going to go into the details, but he had reasonable success to show in his eyes that there was shielding. Others argued not. His worst critic admitted that he was a great experimentalist, but he was criticized because his measurements were at the same level as the accuracy of the equipment. As large and as the cylinder of mercury was and the lead blocks were, they're not as large as the galaxy. And I'm suggesting, could it be that the galaxy is the largest evidence that supports shielding? So now I'm going to use the particle model, and G1 is in the particle model is the gravity particle, and it's coming at the galaxy at the, and I'm only going to discuss the galactic plane. It comes here and passes through, or it interacts, it pushes, or it gets trapped. In any case, it loses as it goes through here, and it loses as it goes the other way. And nominally, you might suggest that it's equal at the center. So then I plotted, this is totally arbitrary, it's my drawing, it has no real numbers, it's just trying to point out some of the, and an interesting point. This vertical column relates to the number of particles per unit time that's flowing at this point throughout the galaxy. And I've only represented the half of the core, the open gap, the first arm, and then another open gap, and then I didn't go to the second arm. But at any rate, if they were nominally equal, and the arrows here are intended to mean that they're nominally equal, as you go from the core out, you're going to lose a lot through the core, a little through the gap, a lot through the first arm, and a little through the next gap. It's the opposite way going this way. You have a lot of them to start with up here, a higher quantity of G1. You use a little, then a lot, a little, then a lot. The interesting point is that it is a compounding effect, because as you go from the core outward, you not only are gaining this way as you go towards the right, you're losing this way. So you have both a gain and a loss. And the net force out here is directly proportional to the number of particles here pushing this way versus the number of particles pushing that way. But now I'm going to go to a different equation. I'm going to rewrite the velocity equation by using Newton's second principle, which says acceleration is equal to force divided by the mass of the object that's moving. That's his second principle. The other half of this equation comes, I believe Christian Huygens did this, and it's that if the acceleration equals the square of the velocity divided by the distance to the center of the object, you then have a circular orbit. Okay, so what I did then was combine these two parts and solve for v squared, and I get a different equation for velocity, which is equal to the square root of the force times the distance divided by the mass. But this is the mass of the object, not the mass of the galaxy. So this force, this doesn't include g. Now it could include g. If I took the force and I put Newton's equation in there, I could just flip it right back to the other equation. But I'm going to leave it this way, and the force is, in this case, I'm intending that the force be a force calculated using shielding. And then R is the distance. I already said that, so I will repeat myself. So in the particle model, back in 2005, late in 2005, David asked me to work on a gravity experiment. To help him with that experiment, I developed an equation. That's the equation that I developed right there. I used it back, and there's a paper on that in the about the experiment and using this equation. And I compared it to Newton's equation, and I got a fairly good match on the shape of the curve, not the values. I didn't get the values right, but I got the shape right. So this is an equation for gravity, but it uses the term here, percent reduction. Okay, so that's the part of this equation that tells you it includes shielding. And then this is the one I just showed you developed. So if you went to a star, a distant star, and calculated the force on that star using this equation, you would be able to plug it in here and calculate the velocity and see if you could match the curve. Now I've done enough of these calculations. I had just a 2-body or a 3-body problem to solve with this. It takes me 2 or 3 months to get everything right, not because I can't get things right, but it's also an iterative process. You can't solve this equation just by multiplying and dividing things. It's an iterative process to get the answer. To solve this equation, and this is only for one object, to solve this for a galaxy, and doing it 3-dimensional, because this is a 3-dimensional equation. I select a plane, I select an angle in the plane. That's a 3-dimensional system. It can be done, believe it, but it is tedious, it's frustrating, and it takes a long time. So I didn't do it for the meeting. I expect it would take me, well, knowing how to do it, would take me probably over a year to complete it, because you got to get all the equations right, all the geometry right, and make sure that's right. Then you got to program it in an equation that does the count, and then you got to iterate it until you get the right answer, that everything works out, and finally you've got it. It would be, the only person who really would want to do that is probably me, because it's my equation. It's a tough job. But that force equation does not use g, it does not use r squared, because the square in this equation is implied in the geometry. And it does work as the square. If you have a simple model, you can see it'll ultimately give you the r squared function. Piece of r is proportional to the mass assigned to the path. So you have to calculate geometrically the amount of mass in each path that you go around. And you can make these paths big or as small as you want. The smaller you make them, the longer the processing takes. But that's where the shielding occurs. So with this force equation and this velocity equation, you calculated, predicting that you can calculate that curve. Now I'm going to do something slightly different with it. I'm going to take Newton's equation and include shielding. And if you do that, what I'm saying is you're either going to, if you use Newton's equation, you either have to accept dark matter or find a physical reason to change g. And I'm saying, yeah, there's a physical reason to change g. And I'm saying g is not constant. So I turned my equation, that equation around that includes G, and I'm going to solve for G on each point of the blue curve. So I took this original graph and I printed it out, I put a grid on it, and I read the data points off of that curve. I turned around and I plotted that on an Excel spreadsheet. This is a piecewise linear curve. It's not very smooth. There's a straight line right there. You can see more of what looks like straight lines. Point 13, it turns out I don't show it, is where our solar system is. So you can see it's basically at the same place on this curve as it was on the original. That's the value, I'm plotting the velocity, which is in kilometers per second over here, against an arbitrary point number, which is, you can relate to the distance. So then I took this equation for G, and I abstracted it to an arbitrary distant star, G sub 0, and just rewrote the equation in terms of its velocity v0, its distance r0, but with the mass of the galaxy. And I did the same thing for our solar system. This is for our solar system. And I'm just giving you the nomenclature for it. But then what I did is I divided the bottom equation into the top equation and restructured it, and you get an equation for G0, which is in proportion to the G sub S of our solar system, with a ratio which compares V squared R of the object to V squared S of our solar system. I assumed the mass was a constant. You see, these are the same, they canceled out. That's the value of G. 0 at the core works its way up. Point 13, where our sun is about 6.67, and that's where that is plotted. So these all these numbers, if you use this number 6.67 as G, you're going to get the right answer. But if you go out to the edge of the galaxy, you have to use this value of G up here to get the correct answer. So we have G sub 0, V sub 0, we have R sub 0, we have all three of those. So now I shouldn't say solve for velocity. I'm trying to get to the point where I can solve for velocity if I knew that value of mass. So let's do that. Let's rearrange the equation again. Now I got the mass of the galaxy equal to any point on the curve. I could pick any point on the curve that has a velocity, has a distance, and pick its corresponding value of G0. And I multiply them out at every point within my accuracy of reading the data points. I get 1.2 times 10 to the 36 kilograms. Now, what's interesting about that, well, the first point to make is what I just did isn't right. It's wrong. You can't really trust that number. The warning says, Newton's equation assumes that the mass is located at the center. The G value assumes mass is distributed. So I'm mixing something that involves all the mass concentrated in the center with something where the mass is distributed. That's not correct. So the number 1.238 is to be taken with a very large grain of salt, because but I thought it was interesting to look at and see what it came out to. So then I looked up the visible mass of the galaxy. In Wikipedia, now taking their words at face value, they estimate 0.8 to 1.5 times 10 to the 12 solar masses in our galaxy. And each one is estimated to be the same as our sun, which is 2 times 10 to the 30th kilograms per star. You multiply that out and you get an estimated mass of 2.3 times 10 to the 42 kilograms. That's the visible mass. That's not dark matter. That's what you can see. So, but here's the interesting thing that it points out. The calculation I did, however wrong you might consider it, did come out less than the visible mass of the galaxy. All I'm saying is, it's a hint that if I had the time to do the force the right way and put it in the right equation, I might be able to get a better answer than this. But to me, it became a very interesting result. However, and you could throw it out, and I won't argue the point. Okay, my conclusion is that mainstream picked the wrong term. They picked M and invented dark matter. And I'm saying that by virtue of shielding and the distributed mass, you may be able to not only explain the velocity at the end of the galaxy, edge of the galaxy, but you may be able to explain that curve. Shielding suggests that the force of gravity changes as you move from the core to the edge of the galaxy. Therefore, G is not a constant. It's my opinion that the shielding and the particle model predicts the shape of the blue curve, and that so therefore the blue curve is a galactic idea, it's data at the galactic level that shielding might be possible. I'm not saying it's absolutely true, but I think it supports that idea. Thank you for your attention.
Questions? I'll go ahead and start. A couple of questions. One, or isn't it the case that the particle model takes in case geometry, right? Takes in case geometry, whereas mainstream's not doing that.
Well, they're taking the real geometry of the system and crunching it down into a point. Newton struggled with that. He didn't like it. There's a nice paper that I gave a report on one time, where he actually didn't think that his theory of gravity, his equation, was valid at the surface of the Earth. He didn't even think that was true. He had to rationalize it by assuming that the Earth itself was a bunch of concentric shells. And that seemed to convince him that as long as your perfect sphere in your model is a homogeneous sphere or concentric shells where each shell was homogeneous, then it worked. So it was very conditional on his mind. And he didn't even think it worked below the Earth. It was all covered in that paper. His model with G collapses all of the mass, which is a huge assumption. Particle model doesn't make the assumption at all. It says, no, it's out there, it's spread out, just like Ray was saying. It's, you got to account for where it is. You can, well, let me just make this comment. You can use Newton's equation, model it as best you can as a real distribution, and piece it up, and then calculate the individual forces all around.
He did that, right? I mean, that's what he did in that one paper a couple of years ago. Is that right?
Cameron.
Yeah, Cameron broke it down into arms.
Yeah.
So really, that's what I'm saying. It seems to be.
So but some people would attempt to do that, but most people don't want to bother. That takes effort. That takes work.
Does that mean we can conclude that he did work? Yeah.
But with the equation I have, it forces you to take care of the geometry. You have no choice. Yeah. If you're going to use that equation, you got to use the geometry. And model it as best you can, even though you can't model it perfectly.
Okay, I have another question. G as a constant, now that you work with the particle model so long, and so if we take the Earth and we move it somewhere else in the galaxy, would our G change?
Yes.
Can you explain why? Or is that another paper?
Generally speaking, because the galaxy is so open, when you move the Earth to another spot, although there's all these little pieces, and you would think, well, now it's totally different. I would think that close by, there would be enough of these particles coming at you to help keep the same amount of gravity right around the surface of the gravity, but that the net force at larger points would be different.
So the question I think is
I think it does change. I think it's changing now, but it's so minor. Every instant at a time, we got a different set of gravities coming at you from 70 sextillion different places.
Is it more related to the Earth, or is it related to what's around it? G.
According to this, you would have to believe it's going to be different when you move. I just don't know how much. Now, this would imply that if you moved it out to the edge of the galaxy, it's going to have a higher velocity. And the Earth, however it got its velocity, doesn't have that high a velocity, so it's stuck in its particular place. And I hope we don't move out there, because I would suspect the gravity would be different if I was on a Earth-like planet out there at the edge.
Okay. Any more questions?
I have two questions. Number one, how did the mercury and the lead shielding work out in whoever's experiment? I don't know how it works. Did they shield the gravity?
Yeah, well, keep hitting this. No, what he had was, he had a balance, a very accurate balance. He had a 1 kilogram lead ball on one side of the balance, another kilogram lead ball on the other side. And he balanced that. It was a rubric balance, is what I remember. And on one part of the balance, the part that turns, he put a light source 12 meters away so he could put the spot on the wall. And he set that up that way without the mercury or without the lead ball, and then he moved the mercury or lead ball, the mercury into place. He dropped it for the cylinder, mercury cylinder, he dropped it to the center and then let it adjust and watch the movement. And since he's doing a balance, he kept relating his measurements to mass. He reported his results in terms of mass. He said mass was decreasing because of the shielding. Well, that got him shot down all over the place because the mass really wasn't changing. It was the it was the force of gravity, if you will, or gravitational acceleration that was changing because of the shielding. And he did the lead cube both at the top of the cube, in the middle of the cube, and below the cube. In all the measurements, he was able to identify that there was a difference. The spot on the wall changed. So he had positive results in his own mind. You read the book, Pushing Gravity, it has a lot on that experiment. There's controversy about whether it was accurate or not. My point here is he did all that work, all that effort to get it right using the mercury cylinder and the lead cube, when maybe we've got data here at the galactic level that we can use and prove the shielding.
Maybe just a comment.
You have to use it.
Oh, okay. Well, just maybe this comment. It seems to me it has always been a mystery, and certainly was a criticism of Newton by people in Newton's time. They said, your law would bound to result in an infinite glob of mass accumulating, because the more mass you have, the greater the pull, there'd be no limit. So why don't we find bodies that are literally infinite in mass? And so the answer is, it would seem, has to be that it doesn't happen that way. At some point, gravity must change, and it must no longer push as hard in the center as it used to. So I think that does argue against, well, it bothers me even about Einstein, because I don't see why there should be a limit to the bending. Well, I guess his light. Well, okay, that was basically.
You bring up an interesting point, though. If you're going to go to the whole universe, and obviously there's more there's space out there there's things out there that we don't know about. But for the ones we know about, you consider the mass here and open space out there. It's a simple model. If there's no mass outside of this, there are no particles coming at the edge of our galaxy, at the edge of the mass. At the edge of the mass, not at the edge of the universe, but at the edge of the mass of this, there's no particles coming. There's only particles pushing out. Think about it. So at the edge, you might have an expanding universe. But when you get down into the center, you have particles both directions. At some point, it sort of equals. At the center, it's compressive. Here, it's equal. Here, it's actually pushing out. That's what the model would say. Whether that's right or not needs to be proved.
May I ask a second question?
We have a question from the internet, so why don't we
Okay,
let them go first?
Be right back.
If G can vary, could the Earth have moved through different values of G over the hundreds of millions of years of geological time?
Well, I wasn't there.
You sure?
Not that old.
Well, it's changing now. The question is, how much does it change? And I go back to this large number. The number I get quoted is that there are 70 sextillion stars in the observable universe. So where did the gravity particles come from? They come from the stars. They're coming from all directions. You make one change in our galaxy where it changes a little bit. How much has that changed relative to 70 sextillion stars all shooting particles at you? Doesn't seem like it would change it much. But yes, theoretically it changes. Now, the problem is I'm also an engineer, and I said, so what? As an engineer, I don't care. You know, I can get the rocket ship to the moon anyway. I got a pilot on board who can make the final adjustments, even when I can't calculate it precisely. But as a physicist, you care. Well, how much effect does it have? I think it's very small because of the large number.
Okay. Suppose it is a galactic plane, and on the plane edge you have a certain value of the G, but put a center vertically up, same distance there. Will the G value the same or different?
It's different. It's different. Assuming the mass distribution is different, it's different. And the question, maybe, I don't know, is our solar system it's in line with the galactic plane to some degree, right?
So in other words, G is a function of mass.
Mass is when the gravity particle goes through a mass, that's a certain percentage is lost. And that's what sets it up. So you could say mass causes it. It causes the differential, but it isn't the force. The force comes from the particle when it actually hits, it pushes and scatters off.
I think in answer to your...
Wait, oh, yeah. And please come close to your
I think in answer to a question that was raised, the plane of our solar system is tilted quite a bit away from the disk.
I didn't know what the angle was.
And I don't have that memorized, but I believe that it's closer to 90 degrees than it is to 0 degrees.
Is that right?
And I think that has a significance which I won't go into now.
Thank you. Thank you for the information. Okay, Charles?
I have a couple of comments. One is we've been measuring the force of gravity for about 300 years, and it's decreasing. But the mass of the Earth is increasing because we have all the asteroids and things like that coming in daily. So it increases the mass, the size of the universe, of the Earth. That's the first comment. The second comment is both Newton and Einstein were asked if they knew what mass was, and they said no. It is a proportionality constant in the equation F equals ma.
Exactly.
And
yes.
so it may, if you knew what mass was, you might be able to say more about these issues, but we have not done that. In my talk on Friday, I will explain what mass is from the electrodynamic perspective, which would be the first definition for mass, as far as I know. The other thing is when you write the force of gravity F equals big G m1 m2 over r squared, and you see the force of gravity is changing over time, it's decaying. Is mass decaying or is G decaying? How do you determine which one it is?
Well, first of all, G is a constant, not a constant, but it's intended to be a constant of proportionality to make Newton's statement work as an equation.
Right, but we've measured it for 300 years and it's been decreasing all the time for 300 years. And if you measure it today in this room, and you measure it tomorrow to 8 significant figures, they won't even agree to 4 significant figures. It varies from day to day.
Yeah, and we're moving from day to day, right? We're spinning, we're orbiting, and other objects are changing.
But no one knows how G depends on that or how mass depends on that.
Well, and I'm not even an advocate of trying to use G at all, okay? The force equation that I have does not use G. It uses shielding or that type of, and we probably agree on what mass is. I've often said that mass is an assigned property because we build this object out of platinum and iridium, and we make it a certain size, and then when we're all done, we take a Sharpie, we write 1 kilogram on it. That's how we assign the value of mass. And we use that value to describe motion. That's the only thing mass is used for. Mass, to me, is not a something that an object has. It's an assigned. We assign it the property of mass to the Earth so we can describe its motion.
Right, and then when we measure that mass, the next day it's different. It was the day we declared it the standard.
Well, have you checked your instruments?
Yes.
No, I'm kidding you.
We have now, our accuracy is now 8 significant figures, and no 2 measurements of gravity agree to more than 3 or 4 significant figures.
Thank you.
Okay, any other questions? Okay, we'll take one more and that's it.
It seems to me that from the interaction between you both, I think we have to redefine what G is, and worse, G has not been defined as anything yet.
Well, then you have models like the particle model that don't even use it. So the question isn't even that, it's whether we even need it. So, I mean, it's useful for calculations, but the question is, we're talking about it and all that, well, if we have an equation or a formula in a model that has no G in it, and it's describing gravity in the right way, then there's the other option of why, you know, we're discussing a constant that's just a crutch for now.
But then NASA sending so many rockets to the space or to the moon, I think G must play a critical role in their calculation.
Yeah. One of the things that's interesting, actually, the model of the solar system they have, it is a incredible hodgepodge. I forget there's a name of it. A hodgepodge of equations with an incredible amount of tweaks and changes. And they constantly have to adjust it because they're never right, because there's too much going on. They don't know what's going on. So they constantly measure it, recalculate it, and then try to come up with some maybe idea, maybe why it's wrong, and go in. So what NASA really spends their time is getting it close, and then when it gets closer, making adjustments as they go along. So we have this idea that NASA knows where everything is, and they don't. And so they use rough analysis, and G works and gets them to the right area, as long as they use the right metric or system, and then they use that to steer to get back on course where they want. So
there's an interesting point I could still make, and I don't, we should probably cut it off, but you look at that extra force at the edge of the galaxy, and then you think about Pioneer 10 and 11 going out of our galaxy, and it's passing through these areas where there's extra force, and we're wondering why they slow down. Think about it.
Okay, that's it.